Good morning, dear students. Today we are going to discuss the video lecture series on thermodynamics 1, that is your laws of thermodynamics. So our outlines in the series are zeroth law of thermodynamics, first law of thermodynamics, and significance and application of first law, steady flow energy equation and steady flow energy equation for nozzle. First, what is zeroth law? Zeroth law tells us the concept of temperature. That is, if two systems are in thermal equilibrium with a third system, then these three systems are also in thermal equilibrium with each other. This is the zeroth law of thermodynamics. Here we explains how if A is in thermal equilibrium with B and A is thermal equilibrium with C, then B and C are also in thermal equilibrium with each other. Here A is thermal equilibrium with B and A is but due to your zeroth law of thermodynamics, these three systems, that is A, B and C, these three systems are also in thermal equilibrium with each other. Means the temperature at the end, we will see that the temperature, if the temperature of A is 25 degrees centigrade, then also the temperature of B is in 25 degrees centigrade and C is in 25 degrees centigrade. So that's why the zeroth law of thermodynamics tells us the concept of temperature. Okay. Next is your first law of thermodynamics. First law of thermodynamics tells us the that the heat absorbed by a system is utilized to do some external work and increase the internal energy of the system. So first law is also stated as the energy can neither be created nor be destroyed. It only transfer from one form to another form. So if in a system we supply some amount of heat, it is utilized to increase the internal energy of the system, that is delta U, and doing some external work. These things will describe here. The first law of thermodynamics is generally represented as U is equal to Q minus W. That is, that I have told here, Q is equal to delta U plus W. Here it is written as U is equal to Q minus W, where U is the change in internal energy, that is the system internal energy, that is delta U, and Q is the heat given to the system. Capital Q is the heat given to the system, and W is the work done by the system. The how much work system will do by the supplying some amount of heat to the system. Significance of first law. What is the significance for the first law? The relationship between heat and work is established by the first law, that we have seen in previous slide, that Q is equal to delta U plus W. So Q is the heat supply and W is the work done. So that's why the heat and work relationship is established by the first law, and both work and heat are equivalent to each other. That also tells us the first law. Next, application of first law, that the first law is mainly applied in case of your heat engine, that is your general engine. First law is applied. The amount of fuel we supply to the engine is utilized to increase the internal energy of the fuel and doing some external work, but we are using it to drive the engine, but drive the vehicle forward. So it is the application of first law is mainly in case of your heat engine or the engine that we are commonly used in various forms. And refrigerators are also some of the example that we have also given for the application of first law. Okay. Next one is the application of first law, that is your steady flow energy equation, which is mainly used to find out the work done for an open system. So for a closed system, we can find out the work done by integration of PdV. W is equal to integration of PdV. But in case of open system, we are going to find out the work done by using your steady flow energy equation. Okay. So what do you mean by steady flow? Or what is a steady flow? Now, the flow is said to be steady flow if the properties like pressure, volume, and temperature do not vary with respect to time. Means if the pressure, volume, and temperature in case of inlet and in case of outlet is same, then it is known as your steady flow. So such type of flow can be observed when mass entering and leaving the system is same. It can be observed in this type of flow. Here we are seeing that in a open system, your mass entering in this side and leaving in this side. It may be opposite. So your if the mass is entering in this side and mass is leaving in this side, so we can calculate here the steady flow energy by applying steady flow energy equation. We calculate the work done by the system. It may be a compressor, maybe a turbine, it may be anything. Okay, so here the your this one is your velocity of the fluid. This is the datum head, that is your Z2. This one is your datum head, that is your Z1, and this is the area of the cross sectional area likewise. So consider an open system in which working fluid flow at a steady rate. The working substance entering the system at section 1.1 we have seen in the previous slide and leaves the system at section 2.2. Let m is the mass flow rate of the fluid, that is in kilojoule per second. P1, P2 are the absolute pressure of the working fluid, and C1, C2 are the velocity of the working fluid. Z1, Z2 is the elevation or the distance above the datum line at the entrance and exit of the fluid respectively. And U1, U2 is the internal energy of the fluid at inlet and outlet respectively. QCV is the amount of heat added to the system, and W is the work done by the system. So here we can see that so energy in is equal to half m C1 square plus mg Z1 plus U1 plus QCV. Energy out is equal to half m C2 square plus mg Z2 plus U2 plus WCV. So W is equal to your minus P1 B1. What is minus P1 B1? Minus P1 B1 is the flow work done by the surrounding to the fluid. The work done by the surrounding to the fluid, that's why this is termed as your minus symbol. If and plus P2 V2 is termed as the work done by the system to the surrounding. Okay, so here we are equating this equation by the inlet and outlet. So in inlet, that is your half m C1 square, that is your kinetic energy, and mg Z1, which is your potential energy, plus U1 internal energy, and the heat added to the system to do some external work. So in case of inlet, that is your half m C1 square plus mg Z1 plus U1 plus QCV. In case of outlet, that is your this one is your kinetic energy, it termed as half m C2 square. This one is your potential energy, termed as mg Z2 plus internal energy plus work done, WCV. So if you supply some heat, there is some work also. The heat is supplied here in term of QCV and the work done is in term of WCV. So half m C1 square plus mg Z1 plus U1 plus QCV is equal to half m C2 square plus mg Z2 plus U2. We can turn WCV as like this. In previous slide we have seen that work done is equal to minus P1 V1 plus WCV plus P2 V2. Okay, so we turned it like this. In WCV we put this equation minus P1 V1 plus WCV plus P2 V2. So term by rearranging this term, so in one term we are keeping in left side and two terms we are keeping in right side. So U1 is here, this P1 V1 is coming to the left side, so U1 plus P1 V1 plus half m C1 square plus mg Z1 plus QCB is equal to two terms on right side, U2 plus P2 V2 plus half m C2 square plus mg Z2 plus WCV. So U1 plus P1 V1 we know as this is your enthalpy, or U1 plus P1 V1, that is your H1. So plus half mc1 square plus mgz1 plus qcv is equal to h2 plus u2 plus p2v2 is termed as your h2. So h2 plus half mc2 square plus mgz2 plus wcv. Dividing the above equation by m on both the side, we can rearrange the equation that h1 divided by h1 divided by m is equal to small h1 plus half m c1 square divided by m. So m get cancelled, that term as half c1 square plus mg z1 divided by m get cancelled, that is term as your gz1, and qcv divided by m. Okay, equal to likewise h2 plus half c2 square plus gz2 plus wcv by m. Okay, so by putting this equation in nozzle, we can determine that. So in case of a nozzle, if you are putting the steady flow energy equation, it is termed as your h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. We know that nozzle is utilized to increase the velocity of a fluid. So in case if you apply the equation, the steady flow energy equation in case of a nozzle, so your equation is becomes h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. As we know that h1 is equal to h2 plus v2 square by 2, and as work done is 0 in case of a nozzle, so v2 square by 2 is equal to h1 minus h2, and if the potential energy that z1 is equal to z2 is equal to z implies the equation becomes v2 is equal to 2 into h1 minus h2 root over. Okay, okay, you can collect more information by going to Professor Sumant Chakravarti, who is the professor of IIT Kharagpur. You can collect more information by going to this site. Thank you.